We are moving ahead with the second lecture in the first week of our classes. The first point being the Avogadro number. This number helps us understand how many particles are present in 1 mole of any chemical, which is 6.022 into 10 to the power of 23 particles per mole. And then we moved on to understand that the molecular mass determination, molecular weight for different types of chemicals. We try to look at sodium carbonate, water and sucrose. In addition to understanding how to determine the molecular mass, we also defined what is chemical stoichiometry. Having defined chemical stoichiometry, we understood what is a limiting reagent and how to determine stoichiometry of different reactants that engage in a chemical reaction. We finished off the lecture by defining the concentration term called molarity. How did we define molarity? Molarity is defined as the number of moles divided by volume of solution in liters. To continue from where we left off, the next unit of concentration that we will be trying to look at today is molality. Let us ask a first question. Since we have already learnt what is molarity, what is the need for learning what is molality? First thing, molarity is dependent on the volume of the solution. So, one has to remember how do we make such solutions. We would end up adding, let us say, solid or liquid to a volumetric flask and make up the volume to a given mark in that given volumetric flask. Let us say we want 100 ml, we take a 100 ml volumetric flask and make it up to that given mark, looking at the lower meniscus or upper meniscus depending upon the solution. However, one has to understand that making up solution in terms of volume has a major limitation in the fact that small variations in temperature could result in differences in volume of the same liquid. It could be that the vapor pressure of a given liquid is different, and you could also have other problems that are associated with it. Therefore, the term molality was introduced, where molality is given by the number of moles present in 1 kg of the solvent, meaning mass of the solvent. In kilograms. So, the major differences that come here is that it is not the volume of the solution, and the other thing of course as I just mentioned, it is not the solution we are looking at, we are looking at the solvent. As we know that the mass is going to be almost invariant with respect to temperature, this is a measurement that would be easy to do. The reason why we are choosing this is to ensure that small variations in temperature do not result in variation in the concentration unit that you are looking at. Okay, so what are the advantages of it? As I mentioned, temperature is one advantage, and the second advantage here is that, let us say you have multiple solutes. So, what will end up happening is that when you have multiple solutes, it does not matter how does the volume of the solvent change. So, basically you are adding the same mass of the solvent here. Therefore, when you are determining molality of a given chemical, it is invariant to other solutes that are present. However, there is a slight disadvantage here. What do we decide as the solvent? For instance, if you are taking a water alcohol mixture and you are dissolving a given solute into it, do you pick the alcohol as a solvent or the water as the solvent? These are things that cloud a little bit of how to use this parameter. So, it has not been used much, but let us take a look at an example as we did yesterday. So, yesterday we took an example of 10.6 grams of sodium carbonate in 500 ml of solution. Remember, I had mentioned it as water, which is a slight mistake. We had assumed there that dissolving 10 grams or 10.6 grams of sodium carbonate doesn't change the volume, which need not be right. And these are the other things that come as an advantage of molality. It doesn't matter how the volumes change, you are adding a certain mass, which ensures that your determination of concentration is fairly accurate. So now going on, the same thing if you are trying to understand, let's say what happens when you dissolve 10.6 grams of sodium carbonate in 500 grams of water. You would realize that this is, as we calculated yesterday, 0.2 molar. On this case, it will be 0.2 molal. So that's the main difference that comes up between these two. But remember, this is a measurement that goes with the mass of the solvent rather than the volume of the solution. So that is the major difference that comes up between molarity and molality. Okay, as we move further, why don't we take a look at a simple reaction? What do I mean by a simple reaction? Is that, let's say you have 1 mole of NaOH and you would like to neutralize it with an acid. So let's take 1 molar of HCl. If you are going to take a certain volume here, let's say you take 20 ml here, you would need about 20 ml, or rather you would exactly need 20 ml of HCl, that is 1 molar, to standardize, or rather to neutralize the sodium hydroxide base. On the other hand, let's say we are trying to neutralize it with sulfuric acid. A simple question that would come up here is that how much volume would be required? And as we are able to see, since there are 2 protons that are present in this acid, you would only need about half of this. So this results in a little bit of tricky understanding of molarity. Basically, when you have 1 molar NaOH, you have equal volume of HCl with 1 molar that neutralizes it, while half of the same concentration of H2SO4 tends to neutralize it. So this brings us to the concept of equivalence. So basically for NaOH and HCl, the equivalence here is 1:1. On the other hand, H2SO4, which tends to have 2 such, basically provides 2 equivalents of H plus. So this is where is the definition of equivalent weight comes into picture. So the equivalent weight is given by the molecular weight, of course, in grams. Equivalent weight is also defined in grams, divided by the number of equivalents. Here, unlike molarity, which doesn't matter what kind of reaction you are using a chemical, this definition of equivalent weight requires what you are going to be using the chemical towards. For instance, let's say you have a chemical that could be used, in this case let's say NaOH, for a neutralization reaction. In case of the neutralization reaction, the number of equivalents is defined as the amount of substance that is required to furnish or quench 1 mole of H plus. So what do we mean by this is that the number of equivalents, in case of H2SO4, it can furnish 2 moles of H plus. On the other hand, when you are looking at HCl, 1 mole of HCl, 1 molar solution of HCl ends up providing providing 1 mole of H plus ions. So this is where the equivalence comes from. What you're able to realize is that for HCl, the number of equivalence is 1. On the other hand, the number of equivalence for H2SO4 is 2. So therefore, what ends up happening, the equivalent weight for HCl is equal to its molecular weight in this reaction. But on the other hand, the equivalent weight of H2SO4 sulfuric acid will be half of its molecular weight. This is important to understand because this gives us a perspective of what is equivalence. Once again, going back to the example that we started with, if you have 1 molar solution of NaOH, if you had 1 molar solution of HCl of equal volume, you tend to neutralize it. On the other hand, if you are having 1 molar solution of NaOH, you just need half the volume that comes up from the equivalent weight of H2SO4 as it furnishes twice the amount of H plus ions. Now, we have defined equivalent weight. The next definition that we would be looking forward is to understand what is normality. Normality, given with the unit N, is defined as number of moles present in a given volume of solution in liters times the number of equivalents. So the major difference that you are able to see here is that unlike molarity, you are actually having yet another term which comes up in the denominator, which is the number of equivalents. As we just saw in a moment back, for HCl and H2SO4, the number of equivalents are different from each other. So for instance, for such a neutralization reaction, a 1 molar HCl solution is 1 normal HCl. On the other hand, a 1 molar H2SO4 solution is 2 normal H plus ions. Okay. We have just seen that number of equivalents has been defined for a neutralization reaction. Let us quickly ponder how this gets defined for a reduction oxidation, that is a redox reaction. Okay, for a redox reaction, the number of equivalents will be equal to the amount of substance that furnishes or quenches, that consumes or produces 1 mole of electrons. Why don't we take a little moment to understand how this is defined for a simple redox reaction. I am sure from your school days you have been doing the titration of oxalic acid with potassium permanganate. What is oxalic acid? Oxalic acid is a diprotic acid where the oxidation state of carbon is +3, and then you are titrating it against potassium permanganate where the oxidation state of manganese is +7. So now when you are using an oxidizing agent against oxalic acid, what is going to end up happening is that the carbon is going to get oxidized. So let us take a look at the reaction of oxalic acid getting oxidized by potassium permanganate. Oxalic acid can be written as C2O42 minus and is becoming carbon dioxide. Here carbon is at +4 state, here carbon is in +3 state. So when you are having something like this, what is going to end up happening is that you are losing electrons that go on the other side. And what also ends up happening here is that you have to balance the reaction on either side. Okay. On the other hand, let us change the color. MnO4 minus is the oxidizing agent, that means it gets reduced, it goes to Mn +2 state. And what you are able to realize here is that it goes from +7 to +2. This indicates it has taken 5 electrons. So in addition to taking this, what you are able to see here, appreciate here, is that you have 6 negative charges on the left side, but +2 charge on the right side. So this indicates that you got to be adding acid in these places. Of course, the other part that's going to end up coming is H2O. So here what is going to end up happening is that to introduce neutrality, one is able to understand that you have 6 negative charges and you have +2, you have to add 8 H plus. And in order to balance this, you have a +4 H2O, that makes it 8 hydrogens on both sides and 4 oxygens, and the neutrality is balanced. What you are able to see here is that the oxalic acid loses 2 electrons, while the permanganate gains 5 electrons. So what is going to end up happening, similar to your LCM and GCD, you got to multiply this by 5, while you got to multiply this by 2. So let's rewrite the reaction. C2O4 this results in mutual cancellation of electrons on both the sides, which gives us an overall balanced reaction of 5C2O42 minus plus 2MnO4 minus plus 16H plus, giving 5CO2 plus 2Mn plus 2 plus 8H2O. Of course, you are able to see the fact that you need about 10 protons here, as oxalic acid has the protons. So if you move the 10 here, what is going to end up happening is that you are going to have 5H2C2O4 plus 2KMnO4 plus, so how many protons you have left? You have 6 protons left. So 6 can be written as 3H2SO4. You need an acid for this redox reaction to happen. It's going to result in 5CO2 plus 2MnSO4 is 8H2O. Remember, there is potassium plus K2SO4. So you have 3 sulfate on the left and 3 on the right side. So now that we have done this, what we are able to realize, the equivalence of oxalic acid is going to be given by molecular weight of oxalic acid divided by 2, while the equivalence of KMnO4 is going to be given by molecular weight of KMnO4 by 5. So this helps you understand the concept of equivalence is dependent upon the reaction that you are putting the chemical through. So without an idea of understanding what reaction you are going to be using the chemical for, you cannot be defining what are the number of equivalents. So far we have seen examples of number of equivalents determined for a neutralization and a redox reaction. Let's go and repeat the same process of understanding number of equivalents for a precipitation reaction. For instance, if the number of equivalents for a precipitation reaction is going to be 1 for a univalent cation or anion, 1 by 2 for a divalent anion or a cation, and 1 by 3 for a trivalent anion or a cation, and so on. So for instance, univalent, what do we mean by univalent? Something like NaCl or silver nitrate or other. So what do we mean by univalence? Let me give some examples of univalent. Something like silver chloride. Divalent, one can think of magnesium chloride. Trivalent, one can think of ferric nitrate. So here the equivalence of iron is going to be 1/3, because it's going to be present as +3, +2 and +1. Okay, so now let's try to generalize overall what is equivalent weight. The equivalent weight of a chemical is the amount of substance that is required to furnish or consume 1 mole of H plus ions, 1 mole of electrons, 1 mole for univalent, 1/2 for divalent, and 1/3 for trivalent. And this is defined depending upon the condition of reaction. So, this is a neutralization reaction, while this is a redox reaction. The last case, it is a precipitation reaction. Okay, so why don't we solve some examples? So, let us say you have to prepare 2 liters of 0.2 normal Na2CO3, the same example as we have been seeing so far, that is sodium carbonate, where the carbonate gets converted to carbon dioxide. This is a very common reaction that has been, I am sure you guys have all performed in your lab practicals, where you determine whether carbonate is your anion by adding a little bit of acid and you get effervescence. The effervescence comes because of the fact you have carbon dioxide that escapes the solution plus H2O. Alright, so it is already balanced to start with. So, now the question is, how do you prepare 0.2 normal of 2 liters? One is able to understand quite clearly, since carbonate is taking 2 equivalents. The number of equivalents of the carbonate is going to be given by 1/2. So, the normality is already given as 0.2, which is going to be equal to the weight, that is in grams. So, we need to understand how much of sodium carbonate to add. I am sure from the last lecture we remember the molecular weight of sodium carbonate is 106 grams per mole, then divided by the molecular weight divided by number of equivalents. So, basically you had the definition of the equivalent weight, and here you are putting the 2 product the number of liters in solution. So, you are going to have weight in grams is going to be given by 0.2 times 106 by 2 times 2, which is going to be 106 by 5, 21.2 grams for 2 liters to make overall concentration of 0.2 normal in this reaction. So, now that we have seen an example of this, we can also try to understand what will be the equivalent weight in case of a precipitation reaction. So, let us take an example of ferric chloride that reacts with silver nitrate to give our favorite silver mirror test, AgCl, which precipitates and forms a beautiful mirror in your test tube, plus ferric nitrate. So, we need to balance this really quickly. So, what is going to end up happening? You need to add a 3 here so that the chlorine gets balanced, and this automatically balances it. In this case, what you are able to realize is that the ion atom is going to be engaging itself, or rather will be using 3 equivalents of a univalent silver ion. So, therefore, the equivalent weight of ion in this case is going to be given by molecular weight of FeCl3 divided by 3. To sum it up, in today's class we have seen 2 more definitions of concentration that could be attributed to chemicals. We started with the molarity yesterday, and then we understood what is molality and the need for it, largely because you wanted to have a temperature independent measurement. And you have normality that brings us to the concept of equivalence, which helps us understand how much to add even before you get started with. How are molarity and normality related? Normality is going to be given by the product of molarity to the number of equivalence, and we just defined in this entire class how the definition of equivalence goes.